Good morning, everyone. Thanks for coming to my talk, Pixel Mode, Improving Soft Moderation of Visual Misleading Information on Twitter. I'm Pujan, and this work is done in collaboration with my colleagues at Boston University and Binghamton University. So let's begin. Uh, Social media platforms such as Twitter and Facebook and TikTok, they applied warning labels as a way to circumvent misleading information in the platforms on different contexts such as the US presidential election, COVID-19, and other state of emergencies. But prior work has found that these labels applied by the platforms, they were not comprehensive, and a lot of misleading information was left unlabeled. For some context, previous work on text-only moderation found that Twitter moderated only 4.3% of potentially misleading tweets. And this motivated us to look at what did moderation look like in terms of visual misinformation. So we found that there was a similar story. For example, you can see there's a tweet on the left that it's spreading a misleading image about the wrong vote count, spreading the narrative that the voting machines were hacked in Germany, which obviously did not happen. So the tweet on the left, it was flagged by Twitter with this warning label about stay informed regarding the election, but there were other tweets which shared the exact same image with the exact same narrative which went unmoderated by the platform. And in fact, we found as part of our study, we quantified that Twitter moderated only around 7.3% of potentially misleading images. So that motivated us to develop a system for improving the state of visual soft moderation on social media platform. So we present Pixel Mode, which is an end-to-end system for improving visual soft moderation on platform. So our image, it takes images that a platform has already deemed to be misleading and that they want to moderate on the platform. So we generate image embeddings, and then we use a vector database for indexing and querying the image embeddings. And after visually similar matches are retrieved, we apply additional step of contextual filtering using optical character recognition. And at the end, we give the platform moderators a much larger pool of images that are basically visually and contextually similar to the image that they initially queried with, and that are candidates for moderation. So this is the overall pipeline of Pixel Mode. So now I'll be going through each of the components. So the first step is we need to encode the image into some sort of embedding. So there are two different ways of going about it. One is syntactic embeddings that use perceptual hashing-based techniques, whereas the other type of embeddings are semantic embeddings that use deep neural network-based techniques to represent the images. We went with syntactic embeddings because the first thing, they are really fast in terms of generating hashes on web scale data, and also we found that syntactic embeddings generally perform better for visual similarity retrieval, which I will describe the results of the overall evaluation later on. And as part of building our system, our goal was to determine which is the best syntactic embedding to use. We experimented with two different syntactic embeddings, p-hash and pdq-hash. Pdq-hash is the embedding that is also used by Facebook, and our goal was to determine how do we assess visual similarity between two set of embeddings. And uh, once these embeddings are generated, we need to determine whether they are similar or not. And in a case of few 100,000 images, we could use pairwise similarity. But doing this on a million scale or even billion scale images, such as in platforms such as Twitter and Facebook, that's not feasible. So we use this vector similarity search based backend known as Milbus. It does this, it eases out the process of storing, indexing, and querying the image embeddings. And in our experiments on image index of 19 million images, querying an image and getting the result, it takes only around 0.3 seconds. And this particular setup was done on a CPU only setting, and Milvus has ways to optimize query and indexing on GPU setting as well. So now we have indexed and retrieved visually similar images. We add this additional layer of contextual matching. So I'll give you some insight on why contextual matching is needed. So for example, there's an image on the left that was flagged by Twitter, and let's assume that they want to identify other images that are similar to these. They might use PIXELMOD or any other visual similarity system as query with this particular image, and we are able to retrieve images like this, which in this case is a correct match because it is exactly distorted, like it's a different version of the same image. But image matching systems also return results like these, which are perceptually similar to the query images, but in the context of moderating this misleading claim about dead voters voting in the election, this cannot be considered a match. So we need this additional layer of contextual matching alongside visual matching. There are multiple advantages of contextual matching. First, we are able to reduce a lot of false positives that are not relevant to the original claim that we want to flag. And also, we found that using contextual matching alongside visual matching, it allows us to explore a much larger visual similarity matching threshold. So prior work, they err on the side of conservative matching threshold because they want to ensure that there are as less false positives as possible. So for example, P has related work, they use a Hamming distance of 6. PDQ has related work, they have used Hamming distance of 40, which are really conservative thresholds. But as I will show you, using this contextual matching contextual matching layer, it allows us to explore a much larger distance for matching, and with that we achieve a much higher coverage and recall. So as the OCR component, we use Google Cloud Vision API, and as part of building the system, we needed to determine how do we compare two different pieces of OCR text and what is the similarity threshold for determining they represent the same context. So before I go into the validation, I'll go through the data sets that we used. So this data set was centered around the 2020 US presidential elections. So we used a data set from from a work called Voter For that was related to election denial related tweets. And we also collected our own data set of around 6 million tweets that were related to the event of US presidential election. We used semantic annotations of Twitter on their own tweets for this. And as control and for adding random images as part of the building the index, we also use the 1% Twitter stream, which contains around 12 million images. So our goal is to simulate a real-time search scenario in Twitter where there are not only election-related images, but images of all sorts. So that way, our total dataset size is 19.7 million images. So the first step was we needed to identify what is the best component to build PIXELMOD with. So on a holdout dataset, we did 5-fold cross-validation, and we came up with this final set of configuration that has the best F1 score. We found that PDQ has can be used with the visual similarity threshold of 90, which is actually the largest similarity threshold the developers of PDQ has themselves recommend for visual similarity matching, and we were able to expand this similarity threshold by using the contextual similarity component that we just discussed. So we have a much detailed idea of what should a visual similarity matching system look like in terms of the configuration, and we compared our system with other techniques that can be used. So in our paper, we have a much detailed evaluation of what the performance looks like. So we compared against deep neural network-based methods, and also a much newer family of methods such as CLIP that has the ability to use multimodal capabilities. So using both text and images, we found that our system consistently outperforms all of these baselines, and we are able to maintain a much higher level of precision without sacrificing on the recall. That makes our system a very good candidate for using for platform use for soft moderation. However, there is a trade-off on the runtime. As you can see, this system is little bit slower because it uses this optical character recognition based component, but this slowdown happens only after visually similar matches are returned, not that it happens during the initial phase of the search. So we argue that a slowdown of 0.2 seconds once every 100 images is a reasonable trade-off for gaining much larger recall along the way. So now we have evaluated the system to be much better for visual similarity search. We applied pixel mode in the wild to identify visual misleading information in the context of US presidential election. So first we built a seed query set of 959 images that were moderated by Twitter, which we know like these are misleading images and they should be flagged. And we used pixel mode to query on this larger data set of 19.7 million image index. And pixel mode, it retrieved 40,000 tweets with images that are both visually and contextually similar to these seed images. By that relation, we expect them to be moderated by Twitter, but we found before that we also did an additional check on the false positive of the system. It was 0.99 percentage. And upon checking the metadata of whether Twitter actually flagged these images that are visually and contextually similar to prior images that they have already moderated, we found only around 2,950 tweets were flagged by Twitter, which amounts to 7.3 percentage. This moderation rate is slightly better than what they had in the case of text-only moderation, but still it is way below par. So we did some additional work on contextualizing what these images are and what moderation looks like in accordance to Twitter's own civic integrity policy. So these images, we manually coded aligning them to Twitter's policy, and we tried to see if there are certain types of images Twitter might be prioritizing. And we found that across all these civic policies, the moderation rate is quite low overall, and specifically in the case of synthetic and manipulated media, which you would assume Twitter would be much more aggressive in applying warning labels on this class of images. It was in fact the second lowest. So our takeaway was the moderation inconsistencies were similar throughout all these categories. So in summary, we present pixel mode as a system that can help platform moderators to identify visually misleading images in the platform. It can help scale the moderation efforts of platform. All we need is a set of seed images, and they can use their existing image index, or they can integrate a vector database such as Milvus to alongside these index for querying and indexing. We demonstrated that this can be used on a real-world scenario of US presidential election to identify more misleading tweets. And we did some additional analysis on how the moderation practices by Twitter were inconsistent within the scope of their own civic integrity policy. You can check out more detailed analysis in the paper. And we also have the data sets and the pixel mode system available publicly. Please feel free to check it out as well. Thank you.